In this video, we'll talk more generally about second order equations and different types of them that we have that we can try to analyze and solve. So a second order equation is one where the highest derivative that we see in the equation is the second derivative. This means that the most general second order equation is of the following form. It is y double prime equals some function of t, y, and y prime. It could be any functions that you want on that side, but your highest derivative is a y double prime, and we'll assume that we can solve out for y double prime here. Like something like y double prime equals e to the y prime times t squared sine of ty. That is a second order equation. Now, unlike first order equations, there aren't too many general methods, or really any general methods, for solving these equations explicitly. Sometimes your best bet ends up being going through systems, which we'll talk about later in this course. But in general, there's no real method for solving this. Like, at least for first order linear, we had a technique that always worked, and we could sort of classify first order equations down to being separable or exact or autonomous and get some results that way. There's not really that sort of idea for second order equations. What we really want to do is narrow down the types of equations that we do know how to solve and know how to distinguish them from other types of equations. Right? If this equation only had a function of t on the right side, we could integrate twice and be done, and that'd be great. But if it doesn't have that, there's y and y primes, then we might be stuck. And so narrowing what we can solve is going to be important. And our first restriction, which is probably not one that's too surprising, is the idea of a linear equation. So a linear second order equation has the form a of t times y double prime plus b of t times y prime plus c of t times y equals some function f of t. This is the same sort of equation as before, right? It's linear in the sense that there's no y terms that are multiplied by each other or inside weird functions. They're just sitting there to the first power. And it's second order because the highest derivative here is the second derivative. In standard form, we just want to get the y double prime term by itself. So you have a y double prime plus a p of t times y prime plus a q of t times y equals some function g of t. This is going to be our standard form for second order linear equation, which is what we're spending all of our time on trying to solve in this unit. We have two more types to classify these things down further. The equation is homogeneous if the function g of t on the right side is 0, and it's non-homogeneous otherwise. And the equation is of constant coefficient, or has constant coefficients, if the functions p of t and q of t are constants. Since they don't really have any dependence on t, they don't actually vary with t. So something like y double prime plus 4y prime minus 7y equals e to the t is a constant coefficient, non-homogeneous second order linear equation. And it turns out we really have to restrict down to this bare minimum case here to actually be able to find easy methods to generate solutions. So every condition we add makes it easier for us to solve. So we'll be developing solution methods for all constant coefficient homogeneous equations and methods for a lot of different constant coefficient non-homogeneous equations. Beyond that, we're kind of stuck. Right? There is no general method like integrating factors for first order equations. So if the coefficient of y prime has a t in it, we might be out of luck. There are very specific cases that we'll be able to solve, but not very many. Spent a lot of time talking about these constant coefficient homogeneous equations and show that that's actually really helpful for trying to solve the corresponding non-homogeneous equations. But that's going to be the extent of what we can actually do with these and guarantee that we know how to find solutions to all these equations. But if you look back to the examples for modeling, those were in fact constant coefficient equations. Some were homogeneous, some were non-homogeneous, but they were all constant coefficient. So we'll be able to figure out ways to develop solutions to those types of equations with the stuff we study here in this section. Those are our restrictive terms for second order equations. We basically need to restrict to constant coefficients, linear, and mostly homogeneous to be able to guarantee we know how to find solutions, and that's what we will work on in the future, is developing those methods to solve those types of problems.